Hi everyone, today we will see the topic IGBT. IGBT means insulated gate bipolar transistor. Just we'll see the data sheet of one IGBT. So one part number that is GT15Q101. It is a silicon N-channel IGBT normally used in high power switching applications and motor control applications. So why we are going for IGBT when we are having MOSFET, BJT and all? Actually IGBT it is a combination of MOSFET and BJT. MOSFET means metal oxide semiconductor field effect transistor and bipolar junction transistor. Normally MOSFET it is used in high frequency application. High frequency low power applications we can use MOSFET. And BJT we can use in high power low frequency applications. And when we want high frequency and high power, we will move for IGBT or insulated gate bipolar junction, bipolar transistor. So it is used in high power and high frequency applications. So I told it is a combination of MOSFET and BJT. So how the symbol will be? We know the symbol of MOSFET, right? This is the gate terminal, drain and source. We know the symbol of transistor also, BJT. This is base, collector and emitter. So we are combining MOSFET BJT. So the input side is similar to MOSFET and output side of IGBT is similar to transistor BJT. So the symbol of IGBT will be input side is similar to a MOSFET, that is gate terminal will be there, and output side it is similar to a transistor. And terminals also it is similar to transistor, that is collector and emitter. So this is the symbol of IGBT. Gate, collector and emitter. Normally IGBT we can use for high voltage AC applications. Inverter, electric vehicles, motor control applications and all we can use IGBT. So as we told, it is a combination of MOSFET and BJT. We can draw the simple working, how it works. So just I will draw one MOSFET. Gate terminal, drain terminal, source. And the drain is connected to base of one PNP transistor. So this will act as the collector of IGBT and this end will act as the emitter of IGBT. Source is getting short with this emitter. So we can see the symbol and the terminals, that is gate, collector, emitter, GCE. That is the terminals of IGBT. So when we are giving an input pulse to your gate, the MOSFET will be getting in the on condition. When your MOSFET is in the on condition, the ID or drain current will start rising. This is being connected to base of your transistor. This transistor base it is connected. So when base current is flowing, the transistor will start conducting. It's just like a switch. The switch is getting closed and the current will start flowing. So the whole device will be in the conducting mode. So we will see the internal diagram of IGBT. So this is the internal diagram of IGBT or the layer structure. So depending on this layer structure, we can classify IGBT into two types. So it is mainly classified to two types. That is punch-through IGBT and non-punch-through IGBT. So what is punch-through IGBT? Suppose your N plus buffer layer is present in the layer diagram. We are adding one N plus buffer layer. It is called as punch-through IGBT. And if it is not present, N plus buffer layer is not present, means it is non-punch-through IGBT. Normally, punch-through IGBTs are used in inverter applications, inverter chopper applications. And non-punch through it is being used in rectifier applications. So here we can see one extra N plus buffer layer is there. So it is a punch through IGBT. Just like MOSFET it will be there. One extra P plus injection layer is there. Above that one N plus buffer layer is there. And N minus drift region. P body region is there and plus N plus region is there. So we can see here it is a combination of MOSFET and transistor. So when you are giving an input, what will happen? So this is a gate terminal. Gate is connected to positive, emitter is negative, and this is your P plus injection layer. Here it is. Here holes are being injected in this layer. So when you are applying positive voltage at this end, normally it will attract electrons. Unlike charges attract, so it will attract the electrons from this P body region and this N minus drift region. So here an accumulation of electrons will be there and a channel will be getting created in the body. And the current will start flowing. So as there is a N channel created here, there is a lot of carriers, lot of electrons in this area. So automatically this will attract the holes from P plus injection layer. So the holes from this P plus injection layer will start moving upwards. That means the current flow will be in this direction. From P plus to N plus, current will start flowing. The electrons will be moving downwards and the holes will be moving upwards. And here a lot of carrier movement will happen and this is called as conductivity modulation in IGBT. And the conduction will happen in IGBT. This is simple working of IGBT. And here we can see I told one MOSFET is there internally and here one NPN transistor you can see. One NPN transistor is there. This is one transistor and another PNP region is there. So another PNP transistor is there. So internally here this side one MOSFET will be there. and this side 2 transistors will be there. So just we can analyze the internal diagram. That is with MOSFET. This is one resistance that is called as drift region resistance. This is being connected to one PNP transistor. This is the collector terminal, this side. And one more transistor is there, that is NPN. This is getting short. This source. This emitter region. Here one resistance will be there. This is getting short. This is the emitter for IGBT. This resistance is called as body resistance, body region resistance. So when you're giving an input pulse, the drain current will increase and the current will start flowing to the base. And this transistor will be getting in the on condition and the current will be flowing towards the base of this transistor. So this also will get in the on condition. So both the transistors are on. Again the collector current of this NPN transistor will be more. It will supply to the base of this transistor. So once you give a small gate pulse, your IGBT will continue to be in the working position. That means continuously the current will be flowing in this loop and the device will be on if you are removing the gate supply also. So we need to nullify the effect of this transistor. For that what we can do, that means in construction itself will be reducing the body resistance. That means we will be shorting this one. These two terminals will be short. That means reduce the body resistance. So it is just short. That is emitter and base of this transistor will be short. If emitter and base of a transistor is short means the transistor will be in off condition. It will not be on. So we can remove this transistor and the final equivalent circuit we can draw with one MOSFET and one PNP transistor. So this is the equivalent circuit for IGBT. Thank you for watching.